It's wild to think about, but 10,000 years of human civilization, agriculture, modern infrastructure, all of it exists in this highly delicate temperature window.
Oh, absolutely. It's an incredibly narrow band.
Right. And the difference between this comfortable, familiar world we live in right now and a world where cities like New York are buried under, a full kilometer of solid ice, it's just 5 degrees.
Yeah, just 5 degrees globally. That is the razor-thin thermal margin separating the world we know today from the depths of a deep ice age.
It really puts the scale of our planet into perspective immediately. And it makes me think about the simple analogy from the material we're looking at today. When you put a kettle on a stove and turn on the burner, you don't stand there debating whether the water is going to get hot.
No, of course not.
You don't argue about the kettle's political affiliation or its ulterior motives. You just accept that heat is being applied and the water is going to boil.
Exactly. Because the laws of thermodynamics, they operate completely independently of our opinions. Heat moves, energy balances, and physical systems respond, regardless of how any of us feel about it.
Which brings us to our mission for this deep dive. Today, we are taking a phrase that is arguably the most politically loaded, emotionally charged phrase of our time, climate change. And we are looking at today's source material to completely strip all that politics away.
Right, taking a totally impartial look at the text.
We're going to dive into the underlying 19th century physics of the whole thing. The author describes this underlying science as being, quote, settled, unglamorous, and about as controversial as the boiling point of water.
I love that phrasing. We will be exploring the pure mechanics of our planet. We'll look at how the Earth stays warm, what alters that delicate energy balance, and crucially, exactly how scientists actually know what they claim to know based on the source.
And if you are listening to this right now, you don't need a background in science to follow along. We are just going to trace the logic step by step.
Yeah, assume absolutely no prior science background. We're breaking it all down.
So I invite you to just relax. Put aside the shouting matches you might see on the evening news and just follow this trail of basic physics and forensic chemistry with us. Let's start with a foundational premise from the text. Why is the Earth the temperature it is in the first place?
Well, it all comes down to a cosmic energy budget, a balance sheet, essentially.
Yes.
The sun pours massive amounts of energy onto our planet every single day.
Right, a constant stream of energy.
Yeah, and because the sun is burning at such an incredibly high temperature, that energy arrives across the vacuum of space primarily as short-wavelength visible light.
Okay, so the Earth absorbs that incoming energy, and as a result, it warms up. But the Earth isn't just a sponge, right? It's also a radiator.
Exactly. It has to send energy back out into cold space. If it didn't, it would just get hotter and hotter until it literally vaporized.
Which would be bad.
Very bad. But because the Earth is much, much cooler than the sun, it radiates that energy in a totally different form. It sends it back out as infrared radiation.
Let's define that real quick, just to be sure we're all on the same page. Infrared is just invisible, longer wavelength light, right?
Yeah, exactly. You can't see it, but you can physically feel it as heat. Like, think about standing near a dark asphalt road at dusk on a summer evening. That heat radiating off the pavement, that's infrared.
Oh, that's a perfect example.
So for the planet's overall temperature to hold steady over thousands of years, the energy coming in as visible sunlight has to perfectly match the energy going out as infrared heat.
Okay, let's unpack this, because this is where the atmosphere comes into play, and it acts like a very specific kind of filter, doesn't it?
It does. See, the atmosphere is completely transparent to incoming sunlight. The visible light sails right through the air and hits the ground.
But when that infrared heat tries to leave, the atmosphere suddenly isn't transparent anymore?
Right. Certain gases in our air are invisible to the short wavelength visible light coming in, but they act like a brick wall to the long wavelength infrared radiation trying to get out.
They catch it.
Yeah, they absorb that outgoing heat and re-emit it in all directions, bouncing a huge portion of it right back down toward the Earth's surface.
I pictured this while reading the notes, and I think it helps. Imagine throwing a tiny, hard golf ball at a chain-link fence. That golf ball is the incoming visible sunlight. It passes right through the holes in the fence and hits the ground.
Makes sense.
But when the Earth tries to throw the energy back into space, the energy is transformed. It's no longer a tiny golf ball. It's a giant, inflated beach ball.
I like this.
When you throw that giant beach ball at the exact same chain link fence, it gets intercepted. It bounces off the metal links, and it comes right back at you.
That is a great visual. And that intercepted heat, the bouncing back of the beach ball, That is the greenhouse effect.
Which the source points out is actually a good thing, right?
Oh, it's a critical thing.
Yeah.
It often gets lost in the noise, but the greenhouse effect is a fundamental necessity for life. Without that chain link fence intercepting the heat, the Earth's average temperature would be roughly minus 18 degrees Celsius.
Wow, minus 18.
Yeah, we would be living on a frozen, totally uninhabitable ball of ice. The planet actually has to warm up more than it otherwise would, just to build up enough infrared pressure for enough of it to finally escape into space and balance the books.
So the existence of the greenhouse effect is what keeps us alive. The problem isn't the blanket itself. The problem is that we are adding more metal to the chain link fence, basically making the holes smaller and smaller.
Exactly. We're turning the dial up, which forces us to look really closely at the specific gases in the atmosphere that are doing this trapping.
And this was a surprising fact from the source for me. Our atmosphere is overwhelmingly made of just two gases, right?
Right. Roughly 78% nitrogen and 21% oxygen. Together, that's 99% of the air we breathe.
And neither of those absorbs infrared heat at all.
Not even a little bit. The visible light sails past them, and the infrared heat sails past them too.
So the only gases that matter for this whole energy budget are the quote-unquote trace gases?
Yeah, things like water vapor, carbon dioxide, methane, and nitrous oxide.
But I got hung up on a statistic here. The source says carbon dioxide makes up only about 400 parts per million of the atmosphere.
That's right.
That is 0.04%, just a tiny fraction. My first thought was, how can something that small actually do anything? How can a fraction of a percent of a gas control an entire planetary system?
It's a super common question, and it comes down to molecular structure and resonance. Molecules of nitrogen and oxygen are simple, tightly bound pairs of atoms. They just don't react to infrared waves.
But the trace gases are different.
Very different. Molecules of trace gases, like carbon dioxide, are physically built in a way that allows them to flex, bend, and vibrate at the exact frequencies of infrared light.
So they're like tuned to it.
Exactly. When that specific wavelength of heat hits them, it's like hitting a tuning fork with a perfect pitch. They soak up the energy.
The text uses a really great visual for this scale, too. Think of a large glass of completely clear water. The water represents the nitrogen and oxygen. If you drop just 2 or 3 tiny drops of dark concentrated ink, which represents the carbon dioxide, into that glass, the whole volume turns cloudy and dark almost instantly.
Right. A tiny concentration of a strong absorber has a massive outsized effect on the whole system.
So it's about the potency of the gas, not just the volume.
Exactly. And to ground this in history, this isn't some new computer modeling discovery. The underlying physics of how carbon dioxide absorbs infrared light was actually married with physical laboratory equipment in the 1850s and 1860s.
Wait, really? That long ago?
Yeah, scientists literally passed light through tubes of gas and measured the heat difference. And the foundational hand calculations for exactly how much the Earth would warm if you doubled the carbon dioxide in the air. Those were published in 1896.
That is wild.
It's incredibly old, deeply solid science.
So the physics is over a century old. We know adding these specific gases thickens the blanket. If the math says more trace gases equal a hotter planet, the next logical question we have to figure out is whether we're actually adding more of them to the sky.
And we have incredibly direct evidence for that. The text points to an observatory sitting high up on the Mauna Loa volcano in Hawaii.
Ah, yes, the famous Keeling curve.
Right. Since 1958, scientists there have been continuously measuring the exact concentration of carbon dioxide in the air.
And it shows a relentless upward climb. Back in 1958, it was at about 315 parts per million. Today, it has shot past 420.
Yep, a very clear trend.
But the line itself has this fascinating little sawtooth pattern every single year. It's not just a straight line.
That sawtooth is amazing. It's essentially the heartbeat of the Earth's biosphere. See, the majority of the planet's landmass and forests are in the northern hemisphere. So every summer, when those forests bloom, they breathe in massive amounts of carbon dioxide to build leaves and wood, causing the global CO2 level to drop a tiny bit.
And then in the winter.
Every winter, as the leaves fall and decay, the forests breathe that carbon back out and the line ticks back up.
But beneath that planetary breathing, the baseline just keeps rising year after year. And to get a deeper historical context, scientists go to the ice caps, right?
Right. When snow falls in places like Antarctica, it traps microscopic bubbles of air. As that snow gets compressed into ice over millennia, it creates a vertical timeline of the ancient atmosphere.
A literal time capsule.
Exactly. And analyzing the air in those deep ice cores shows that carbon dioxide levels have now shot far above anything seen in at least the last 800,000 years.
Wow. 800,000 years.
And it is rising faster than anything in that entire geological record.
Okay, so the gas traps heat, and the gas is going up rapidly. But we still need to prove the source. I mean, to play devil's advocate here, how do scientists know for sure that this massive spike in carbon dioxide is coming from humans? Could it just be, the Earth venting carbon naturally from volcanoes or deep ocean vents?
What's fascinating here is that scientists rely on a beautiful piece of forensic chemistry to answer this. It all has to do with isotopes.
Let's define isotopes for the listeners.
So, think of isotopes as different varieties of an element. Carbon atoms are chemically identical to one another in how they react, but they can have slightly different physical weights or masses.
Right, like carbon-12, carbon-13, and carbon-14.
Exactly. Now, millions of years ago, ancient plants absorbed carbon from the air. When those plants died, they were buried and compressed over eons, eventually turning into coal, oil, and natural gas.
Fossil fuels.
Right. And because of the way plants process carbon during photosynthesis, the carbon inside them is naturally depleted in the heavier isotopes.
They prefer the lighter carbon.
They do. And more importantly, that ancient buried carbon contains absolutely zero carbon-14.
Because carbon-14 is radioactive, right?
Yes, it's a radioactive isotope that slowly decays over time. Because fossil fuels have been buried underground for tens of millions of years, all of their carbon-14 has completely decayed away. There's none left.
Oh, wow. So it's basically dead carbon.
Exactly. So as we spend the last century and a half digging up and burning those fossil fuels, we pump that very specific dead carbon into the sky.
And what happens when we measure the air today?
When we analyze the atmosphere today, the overall carbon signature has shifted. It matches the exact isotopic signature you would expect if you were flooding the air with old, dead plant carbon. It's lighter, and the radioactive fraction is highly diluted.
So the extra carbon dioxide wears our fossil fuel fingerprint.
It is a chemical smoking gun.
And the math of the Earth's natural system supports this perfectly, too. The text mentions that the amount of CO2 accumulating in the atmosphere is only about half of what humanity actually emits. The oceans and the land are absorbing the other half.
Right. Nature is a net sink, not a source.
We are putting it into the air faster than the planet can scrub it out.
The mechanism is proven, and the chemical fingerprint is undeniably ours.
Okay, so a 19th century lab tube shows CO2 traps heat, and chemical signatures prove we're filling the atmosphere with it. But a lab tube isn't a planet. Are we actually seeing the Earth's thermometer respond the way that century-old math predicted?
We absolutely are. Global average surface temperatures have risen roughly 1.2 degrees Celsius since the late 1800s.
And that's confirmed across the board?
Yes, by independent lines of evidence. We're talking thermometers on land, sensors deep in the sea measuring ocean heat content, shrinking glaciers, rapidly rising sea levels, and biological markers like the consistently earlier arrival of spring.
Here's where it gets really interesting. An honest skeptic might look at that 1.2 degrees and say, well, the climate has always changed. Ice ages have come and gone naturally long before humans ever built a combustion engine.
A very common and fair question.
Right, so how do scientists know this specific warming isn't just a natural cycle, like a wobble in the Earth's orbit or the sun getting hotter?
Answering that relies on a field of science called attribution, which is the meticulous process of isolating causes. Scientists know that natural drivers exist. The Earth's orbit wobbles, the sun's output fluctuates, and massive volcanic eruptions alter the atmosphere.
And because we can measure those phenomena, we can calculate exactly what they should be doing to our temperature right now.
Exactly. We can test the natural variables independently of the human ones.
So what happens when we run those calculations?
The math simply doesn't support natural warming. The orbital cycles of the Earth are currently, if anything, slowly nudging our planet toward a cooling phase.
Oh, really?
Yeah. And the sun's energy output has been largely flat or even slightly down over the exact same period where our temperatures have risen the fastest.
What about volcanoes?
Volcanoes throw ash into the sky that blocks the sun, causing short-term cooling blips, not decades of sustained warming. Adding up every natural driver simply cannot explain the warming we observe.
The math only matches reality when you add the human-made greenhouse gases back into the models.
That's right.
And the source mentions an ultimate proof here, a literal atmospheric fingerprint. If the sun were suddenly burning hotter and causing global warming, the extra heat would be coming from the outside in. The entire atmosphere, from the top down to the surface, would warm up together.
But that's not what we see. Because the warming is caused by greenhouse gases forming a blanket near the surface, they trap the heat down low.
Right.
As a result, we observe the lower atmosphere rapidly warming up, while the upper atmosphere is actually cooling down because that outgoing heat is intercepted before it can reach it.
That is incredible.
It is an unambiguous, undeniable fingerprint that the warming is coming from a blanket trapping heat from the inside, not from a hotter sun on the outside.
You really can't fake a cooling upper atmosphere.
No, you can't.
So we've established human-driven warming. But the Earth is a complex, chaotic system. And a little bit of warming doesn't just stop there. It triggers other mechanisms that make it snowball, which the source describes as self-amplifying feedback loops. Could you explain what that means?
Sure. A feedback loop is basically a chain reaction. A primary example involves water vapor. We established that carbon dioxide warms the air, right?
Right.
Well, warmer air physically has the capacity to hold more moisture. The basic physics dictate that as air temperature rises, it expands its capacity to hold water vapor. And water vapor is itself a potent greenhouse gas.
Ah, I see.
So a little warming from CO2 causes more water to evaporate from the oceans, raising the humidity, trapping even more heat, and warming the air further.
Which holds more water, which traps more heat.
Exactly. It feeds itself.
And the text gives another clear, everyday example involving ice.
Yes, the albedo effect.
Yeah.
Bright white ice is highly reflective. It acts like a mirror, bouncing incoming visible light back out into space before it can warm the Earth.
But as the planet warms, that ice melts.
Right. And when it melts, it exposes the dark blue ocean, or the dark land underneath. Those dark surfaces absorb light instead of reflecting it. So the area gets hotter, melting more ice, exposing more dark surface.
And the source notes that these feedbacks are so powerful, they roughly double the warming that the carbon dioxide would cause on its own.
Yeah, they amplify the whole system.
So what does this all mean for you and me? The text says we've warmed about 1.2 degrees Celsius. Maybe we hit 1.5 or 2 degrees. To an average listener, the difference between, say, 20 degrees and 22 degrees on a thermometer sounds negligible. It's like the difference between wearing a sweater or a t-shirt. Why should anyone care about a tiny shift in a global average?
It's a great question because our brains just aren't wired to think globally. A global average is a, quote, vast, sluggish quantity.
Right. It takes a lot to move it.
Enormous energy. To move the average temperature of the entire atmosphere and all the oceans of the Earth by even a single degree requires a truly incomprehensible amount of thermal energy. We go back to that Ice Age comparison from the beginning.
The 5 degrees.
Yeah. Just 5 degrees separated our modern, comfortable world from a kilometer of ice crushing what is now Canada and Europe. A degree or two of warming isn't about a mildly warmer Tuesday afternoon. It is a fundamental shift in the baseline operating conditions of the planet.
The text uses the analogy of loading the dice.
Exactly. It loads the dice for extreme events. Because a warmer baseline means there is vastly more thermal energy and moisture pumping through the entire weather system.
When you load the dice, a heat wave reaches higher peaks than it ever could before.
Right. And a drought bites harder and lasts longer because the hotter air evaporates more moisture from the soil.
And conversely, because that hot air is holding all that extra water vapor, when it finally does rain, the heaviest downpours become significantly heavier, leading to catastrophic floods.
Exactly. The source specifically points to Australia to illustrate why these loaded dice matter so deeply. It's a continent already naturally hot, dry, and prone to massive bushfires and devastating floods.
So if you shift the baseline even a little bit in a place like that,
the extremes get magnified to a point where human infrastructure just struggles to cope. The consequence isn't a slow, gentle warming, it's an escalation of volatility.
Looking back at the trail of evidence we've followed today, the narrative from this source is incredibly clear. Heat-trapping gases keep us alive. We are adding them to the atmosphere faster than at any time in the deep geological record. Forensic chemistry using isotopes proves without a doubt that the extra gas belongs to us.
Yep.
The planet is warming precisely as 19th century physics dictated it would. And those feedback loops are doubling the effect.
And this brings us to a crucial distinction the author makes, and it's a great way to summarize all this, separating the physics from the policy.
Right, because we are strictly looking at the source material objectively here.
Exactly. We can debate all day long about what humanity should actually do about this. The economic costs of transitioning to green energy, the trade-offs of different technologies, the fairness of it all, how fast we need to move. Those are real, highly valid debates that society must have.
But the underlying physics is not up for debate.
No, it's not. The basic mechanics were worked out with glass tubes, laboratory equipment, and handwritten calculations more than a century ago. Everything we have measured since confirms it. It's not a matter of opinion, it's just heat and where it goes.
The evidence is written in the ice, in the oceans, and in the air itself.
Absolutely.
Well, to wrap up this deep dive, I want to leave you with a final thought to mull over. The next time you walk outside and look up at a clear blue sky, think about that invisible boundary high above you, that place where the lower atmosphere is trapping heat and warming up, while the upper atmosphere is quietly cooling down in the dark.
It's kind of haunting when you picture it.
It really is. It is not just a weather pattern. It is a literal physical signature of human history written right into the air. Which makes you wonder, what other invisible fingerprints might we be leaving on the world without even realizing it?